I had a big argument with Sarah about time. She's like, no, time doesn't exist. I'm like, no, time does exist. And now, and as she realized that her conception of assembly theory and my conception of assembly theory were the same thing, necessitated us to abandon the fact that time is eternal, to actually really fundamentally question how the universe produces combinatorial novelty.
So time is fundamental for assembly theory. I'm just trying to figure out where you and Sarah converge.
So I think assembly theory is fine in this time right now, but I think it helps us understand that something interesting is going on. So there's, and I've been really inspired by a guy called Nick Gizzen. I'm going to butcher his argument, but I love his argument a lot. So I hope he forgives me if he hears about it. But basically, if you want free will, time has to be fundamental. And we can go, if you want time to be fundamental, you have to give up on Platonic mathematics, and you have to use intuitionist mathematics. By the way, and again, I'm going to butcher this, but basically, Hilbert said that infinite numbers are allowed, and I think it was Brouwer said no, you can't. All numbers are finite. So they're kind of like So let's go back a step, because it was like people are going to say, assembly theory seems to explain that large combinatorial space allows you to produce things like life and technology. And that large combinatorial space is so big, it's not even accessible to a Sean Carroll, David Deutsch multiverse. That physicists saying that that all of the universe already exists in time is provably, that's a strong word, not correct. That we are going to know that the universe as it stands, the way the present builds the future, so big, the universe can't ever contain the future. And this is a really interesting thing. I think Max Tegmark has this mathematical universe where he says, the universe is kind of like a block universe. And I apologize to Max if I'm getting it wrong, but people think you can just move. You have the initial conditions, and you can run the universe right to the end and go backwards and forwards in that universe. That is not correct.
Well, let me load that in. The universe is not big enough to contain the future.
Yeah. That's why. That's it.
So that's a beautiful way of saying that time is fundamental.
Yes, and you can have, and this is why the law of the excluded middle, something is true or false, only works in the past. Is it going to snow in New York next week or in Austin? You might in Austin say probably not. In New York, you might say yeah. If you go forward to next week and say, did it snow in New York last week, true or false, you can answer that question. The fact that the law of the excluded middle cannot apply to the future explains why time is fundamental.
Well, I mean, that's a good example, intuitive example, but it's possible that we might be able to predict, whether it's going to snow if we had perfect information.
I think
you're saying it not.
Impossible. Impossible. So here's why. Yeah. I'll make a really quick argument. And this argument isn't mine. It's Nick's and a few other people.
Can you explain his view on time being fundamental?
Yeah. So I'll give my view, which kind of resonates with his. But basically, it's very simple. Actually, it would say that free will, your ability to design and do an experiment, is exercising free will. So he used that thought process. But I never really thought about it that way, and that you actively make decisions. I do think that. I used to think that free will was a kind of consequence of just selection, but I'm kind of understanding that human free will is something really interesting. And he very much inspired me. But I think that what Sarah Walker said that inspired me as well, that these will converge, is that I think that the universe is very big, huge, but actually the place that is largest in the universe right now, the largest place in the universe is Earth.
Yeah, I've seen you say that, and boy, does that That's an interesting one to process. What do you mean by that? Earth is the biggest place in the universe.
Because we have this combinatorial scaffolding going all the way back from Luca. So you've got cells that can self-replicate. And then you go all the way to terraforming the Earth. You've got all these architectures, the amount of selection that's going on, biological selection, just to be clear, biological evolution. And then you have multicellularity, then animals and abstraction. And with abstraction, there was another kick because you can then build architectures and computers and cultures and language. And these things are the biggest things that exist in the universe because we can just build architectures that couldn't naturally arise anywhere. And the further that distance goes in time, and this kind of it's gigantic. And
from a complexity perspective.
Yeah.
Okay, wait a minute. But I mean, I know you're being poetic, but how do you know there's not other Earth-like? Like, how do you know? You're basically saying Earth is really special. It's awesome stuff as far as we look out. There's nothing like it going on. But how do you know there's not nearly infinite number of places where cool stuff like this is going on?
I agree. And I would say, I'll say again that Earth is the most gigantic thing we know in the universe combinatorially. We know. Now,
okay, yeah.
Now, I guess, this is just purely a guess. I have no data, but other than hope. Well, maybe not hope. I have some data that every star in the sky probably has planets.
Yep.
And life is probably emerging on these planets. But the amount of contingency that is associated with life is that I think the combinatorial space associated with these planets is so different. Our causal cones are never going to overlap, or not easily. And this is the thing that makes me sad about alien life, why we have to create alien life in the lab as quickly as possible.
Yeah.
Because I don't know if we are going to be able to build architectures that will intersect with alien intelligence and architectures.
And intersect, you don't mean in time or space?
Time and the ability to communicate.
So the ability to communicate.
Yeah. My biggest fear in a way is that life is everywhere, but we become infinitely more lonely because of our scaffolding in that combinatorial space. Because it's so big. And
so you're saying the constraints created by the environment that led to the factory of Darwinian evolution are just like this little tiny cone in a nearly infinite combinatorial space. And
exactly.
So there's other cones like it, and why can't we communicate with other? Like, just because we can't create it doesn't mean we can't appreciate the creation, right? Like detect the creation.
I truly don't know, but it's an excuse for me to ask for people to give me money to make a planet simulator.
Yeah, right.
If I can make
with a different kind of
like another shameless say, it's like, give me money, I need money.
This was all a long plug for a planet simulator.
It's like
hey, I will be the first in line to donate.
My Rick garage has run out of room.
Yeah.
No.
And this is a planet simulator. You mean like a different kind of planet?
Yeah.
With different sets of environments and pressures.
Exactly. If we could basically recreate the selection before biology, as we know it, that gives rise to a different biology, we should be able to put the constraints on where to look in the universe. So here's a thing. Here's my dream.
Yeah.
My dream is that by creating life in the lab, based upon constraints we understand, like let's go for Venus type life or Earth type life or something. Again, do Earth 2.0. Screw it. Let's do Earth 2.0. And Earth 2.0 has a different genetic alphabet. Fine. That's fine. Different protein alphabet, fine. Have cells and evolution, all that stuff. We will then be able to say, okay, life is a more general phenomena. Selection is more general than what we think is the chemical constraints on life. And we can point to James Webb and other telescopes at other planets that we are in that zone that we are most likely to combinatorially overlap with, right? So, because, we so there is chemistry.
You're looking for some overlap,
and then we can then basically shine light on them literally, and look at light coming back, and apply advanced assembly theory to general theory of language that we will get, and say, we in that signal, it looks random, but there's a copy number. Oh, this random set of things that shouldn't be, that looks like a true random number generator, has structure as a not Kolmogorov AIT type structure, but evolutionary structure given by assembly theory. And we start to, but I would say that because I'm a shameless assembly theorist.
Yeah, it just feels like the cone. I might be misusing the word cone here, but the width of the cone is growing faster. Is growing really fast to where eventually all the cones overlap. Even in a very, very, very large combinatorial space. It just, but then again, if you're saying the universe is also growing very quickly in terms of possibilities,
I hope that as we build abstractions, one idea is that as we go to intelligence allows us to look at the regularities around us in the universe, and that gives us some common grounding to discuss with aliens. And you might be right that we will overlap there, even though we have completely different chemistry, literally completely different chemistry. That we will be able to pass information from one another, but it's not a given. And I have to kind of try and divorce hope and emotion, away from what I can logically justify.
But it's just hard to intuit a universe where there's nearly infinite complexity objects, and they somehow can't detect each other.
But the universe is expanding. But the nice thing is that I would look. You see, I think Carl Sagan did the wrong thing. Well, not the wrong thing. He flicked the Voyager probe around and a pale blue dot. Said, "Look how big the universe is." I would have done it the other way around and said, "Look at the Voyager probe that came from the planet Earth, that came from Luca. Look at how big Earth is."
That it produced that.
It produced that.
Yeah, and
that I think is like completely amazing. And then that should allow people on Earth to think about, well, probably we should try and get causal chains off Earth onto Mars, onto the moon, wherever. Whether it's human life or Martian life that we create, it doesn't matter. But I think this combinatorial space tells us something very important about the universe. And that I realized in assembly theory that the universe is too big to contain itself. Yeah. And I think this is, and now coming back, and I want to kind of change your mind about time, because I'm guessing that your time is just a coordinate.
Yeah.
So I'm gonna change your.
I'm guessing you're one of those.
I'm gonna change one of those. I'm gonna change your mind in real time, or at least attempt.
Oh, in real time. There you go. I already got the tattoo, so this is gonna be embarrassing if you change my mind.
But you can just add an arrow of time onto it, right?
Yeah, true. Just modify
or erase it a bit.
Yeah.
So, and the argument that I think that is really most interesting is, like, people say the initial conditions specify the future of the universe. Okay, fine. Let's say that's the case for a moment. Now let's go back to Newtonian mechanics. Now, the uncertainty principle in Newtonian mechanics is this. If I give you the coordinates of an object moving in space and the coordinates of another object, and they collide in space, and you know those initial conditions, you should know exactly what's going to happen. However, you cannot specify these coordinates to infinite precision. Now, everyone said, this is kind of like, the chaos theory argument. No, it's deeper than that. Here's a problem with numbers. This is where Hilbert and Brouwer fell out. To have the coordinates of this object, a given object as it's colliding, you have to have them to infinite precision. That's what Hilbert says. He says, no problem, infinite precision is fine. Let's just take that for granted. But when the object is finite and it can't store its own coordinates, what do you do? So in principle, if a finite object cannot be specified to infinite precision, in principle, the initial conditions don't apply.
Well, how do you know it can't store its...
Well, how do you store an infinitely long number in a finite size?
Well, we're using infinity very loosely here.
No, we're using...
Infinite precision, I mean, not loosely, but...
Very precisely.
So you think infinite precision is required
Well, let's take the object. Let's say the object is a golf ball.
Mm-hmm.
Golf ball is a few centimeters in diameter. We can work out how many atoms are on the golf ball, and let's say we can store numbers down to atomic dislocations.
Mm-hmm.
So we can work out how many atoms there are in the golf ball, and we can store the coordinates in that golf ball down to that number. But beyond that, we can't.
Mm-hmm.
Let's make the golf ball smaller. And this is where I think that we get randomness in quantum mechanics. And some people say you can't get randomness in quantum mechanics, it's deterministic. But this is where we realize that classical mechanics and quantum mechanics suffer from the same uncertainty principle. And that is the inability to specify the initial conditions to a precise enough degree to give you determinism. The universe is intrinsically too big, and that's why time exists. It's non-deterministic. Looking back into the past, you can use logical arguments, because you can say, was it true or false? You already know. But this is the fact we are unable to predict the future with the precision is not evidence of lack of knowledge. It's evidence the universe is generating new things.
Okay, so to you, first of all, quantum mechanics, you could just say statistically what's going to happen when two golf balls hit each other.
Statistically, but sure, I can say statistically what's going to happen, but then when they do happen, and you keep nesting it together, you can't. I mean, it goes almost back to look at. Let's think about entropy in the universe. So how do we understand entropy change? Well, we could do a process. We can use the ergodic hypothesis. We can also have the counterfactuals, where we have all the different states,
mm-hmm.
and we can even put that in the multiverse,
mm-hmm.
right? But both those are kind of they're non-physical.
Mm-hmm.
The multiverse kind of collapses back to the same problem about the precision.
Mm-hmm.
So all if you accept you don't have to have true and false going forward into the future, the real numbers are real. They're observables.
I'm trying to see exactly where time being fundamental sneaks in this difference between the golf ball can't contain its own position perfectly precisely. How that leads to time needing to be fundamental.
Let me I have a question. Do you believe or do you accept you have free will?
Yeah, I think at this moment in time, I believe that I have free will.
So then you have to believe that time is fundamental.
I understand that's a statement you've made.
That we can logically follow, because if you don't have free will, so like if you're in a universe that has no time, the universe is deterministic. If it's deterministic, then you have no free will.
I think the space of how much we don't know is so vast that saying the universe is deterministic and from that jumping there's no free will is just too difficult of a leap.
No, I logically follows. No, I don't disagree. It's not. I'm not saying any. I mean, it's deep and it's important. All I'm saying, and it's the difference to. It's actually different to what I've said before, mm-hmm. is that if you don't require Platonistic mathematics and accepts that non-determinism is how the universe looks, and that gives us our creativity in the way the universe is getting novelty. It's kind of really deeply important in assembly theory, because assembly theory starts to actually give you a mechanism why you go from boring time, which is basically initial conditions specify everything, to a mismatch in creative time. And I hope we'll do experiments. I think it's really important I would love to do an experiment that proves that time is fundamental and the universe is generating novelty. I don't know all the features of that experiment yet, but by having these conversations openly and getting people to think about the problems in a new way, mm-hmm. better people, more intelligent people with good mathematical backgrounds can say, oh, hey, I've got an idea. I would love to do an experiment that shows that the universe is too big for itself going forward in time. And I really, this is why I really hate the idea of the Boltzmann brain. The Boltzmann brain makes me super kind of like, everyone's having a free lunch. It's like saying, It's like, well, let's break all the laws of physics. So a Boltzmann brain is this idea that in a long enough universe, a brain will just emerge in the universe as conscious. And that neglects the causal chain of evolution that required to produce that brain. And this is where the computational argument really falls down, because the computationists can say, I can calculate the probability of a Boltzmann brain. And I can, and they'll give you a probability, but I can calculate the probability of a Boltzmann brain, 0.
Just because the space of possibilities is so large.
Yeah, it's like when we start fooling ourselves with numbers that we can't actually measure and we can't ever conceive of. I think it doesn't give us a good explanation. And I want to explain why life is in the universe. I think life is actually novelty miner. Life basically mines novelty almost from the future and makes it actualizes it in the present.
Okay. Life is a novelty miner from the future that is actualized in the present.
Yep. I think so.
Novelty miner. First of all, novelty. What's the origin of novelty? When you go from boring time to creative time, where's that? Is it as simple as randomness, like you're referring to?
I'm really struggling with randomness, because I had a really good argument with Yasha Bark about randomness, and he just said randomness doesn't give you free will. That's insane, because you'd just be random.
Yeah.
But I think he's right at that level.
Yeah.
But I don't think he is right on another level. And it's not about randomness. It's about constrained. I'm going to sound like constrained opportunity. I'm making this up as I go along. So making this up. Constrained opportunity. So what I mean is so you have to have, so the novelty, what is novelty? This is what I think is a funny thing. If you ever want to discuss AI, why I think everyone's kind of gone AI mad, is that they're misunderstanding novelty. But let's think about novelty. You ask, what is novelty? So I think novelty is a genuinely new configuration that is not predicted by the past, right? And that you discover in the present, right? And that is truly different, right? Now, everyone says that some people say that novelty doesn't exist. It's always with precedent. I want to do experiments that show that that is not the case. And it goes back to a question you asked me a few moments ago, which is, where is the factory?
Yeah.
Right? Because I think the same mechanism that gives us a factory gives us novelty. And I think that is why I'm so deeply hung up on time. Of course I'm wrong, but how wrong? And I think that life opens up that combinatorial space in a way that our current laws of physics, although as contrived in a deterministic initial condition universe, even with the get out of the multiverse, David Deutsch style, which I love, by the way, but I don't think is correct. But it's really beautiful.
Multiverse.
The David Deutsch's conception of the multiverse is kind of like given. But I think that the problem with wave particle duality and quantum mechanics is not about the multiverse. It's about understanding how determined the past is. Well, I don't just think that. Actually, this is a discussion I was having with Sarah about that, right? Where she was like, I think we've been debating this for a long time now, about how do we reconcile novelty, determinism, indeterminism.
So okay, just to clarify, both you and Sarah think the universe is not deterministic.
I won't speak for Sarah, but roughly I think that the universe. I think the universe is deterministic, looking back in the past,
right?
But undetermined going forward in the future. Yeah. So I'm kind of having my cake and eating it here. This is because I fundamentally don't understand randomness, right? Yeah. As Yasha told me, or other people told me. Right. But if I adopt a new view now, which the new view is the universe is just non-deterministic, but I'd like to refine that and say the universe appears deterministic going back in the past, but it's undetermined going forward in the future. So how can we have a universe that has deterministically looking rules that's non-determined going into the future? Yep. It's this breakdown in precision in the initial conditions. And we have to just stop using initial conditions and start looking at trajectories and how the combinatorial space behaves in an expanding universe in time and space. And assembly theory helps us quantify the transition to biology. And biology appears to be novelty mining because it's making crazy stuff. You know, that we are unique to Earth, right? That there are objects on Earth that are unique to Earth that will not be found anywhere else because you can do the combinatorial math.
What was that statement you made about life is novelty mining from the future?
Yeah.
What's the little element of time that you're introducing there?
So what I'm kind of meaning is because the future is bigger than the present.
Yeah.
In a deterministic universe, how do you go from the how do the states go from one to another? I mean, there's a mismatch, right?
Yeah.
So that must mean that you have a little bit of indeterminism, whether that's randomness or something else. I don't understand. I want to do experiments to formulate a theory to refine that as we go forward that might help us explain that. And I think that's why I'm so determined to try and crack the non-life to life transition, looking at networks and molecules, and that might help us think about it, the mechanism. But certainly the future is bigger than the past in my conception of the universe and some conception of the universe. And
by the way, that's not obvious, right? That's what was just kind of the future being bigger than the past. Well, that's one statement, and the statement that the universe is not big enough to contain the future is another statement.
Yeah.
That one is a big one.
That
one's a really big one.
I think so. I think it's entirely because look, we have the second law, and right now, I mean, we don't need the second law if the future's bigger than the past. It follows naturally,
right?
So why are we retrofitting all these sticking plasters onto our reality to hold on to a timeless universe?
Yeah, but that's because it's kind of difficult to imagine the universe that can't contain the future.
But isn't that really exciting?
It's very exciting, but it's hard. I mean, we're humans on Earth, and we have a very kind of 4-dimensional conception of the world, of 3D plus time. It's just hard to intuit a world where, what does that even mean? A universe that can't contain the future.
Yeah, it's kind of crazy,
weird.
But obvious.
It's weird. I mean, I suppose it sounds obvious, yeah, if it's true.
But the nice thing is you can. So the reason why assembly theory turned me onto that was that let's just start in the present and look at all the complex molecules and go backwards in time and understand how evolutionary processes gave rise to them. It's not at all obvious that Taxol, which is one of the most complex natural products produced by biology, was going to be invented by biology. It's an accident. You know, Taxol is unique to Earth. There's no Taxol elsewhere in the universe. And Taxol was not decided by the initial conditions. It was decided by this kind of this interplay between the past simply is embedded in the present. It gives some features, but why the past doesn't map to the future one-to-one is because the universe is too big to contain itself. That gives space for creativity, novelty, and some things which are unpredictable.
Well, okay, so given that you're disrespecting the power of the initial conditions, let me ask you about, so how do you explain that cellular automata are able to produce such incredible complexity given just basic rules and basic initial conditions?
I think that this falls into the Brouwer-Hilbert trap. So how do you get a cellular automata to produce a complexity? You have a computer, you generate a display, and you map the change of that in time. There are some CAs that repeat, like functions. Like, it's fascinating to me that for pi, there is a formula where you can go to the millionth decimal place of pi and read out the number without having to go there. But there are some numbers where you can't do that. You have to just crank through. There's whether it's Wolframian computational irreducibility or some other thing, well, it doesn't matter. But these CAs, that complexity, is that just complexity or a number that is basically you're mining that number in time? You know, is that just a display screen for that number, that function?
Well, can't you say the same thing about the complexity on Earth then?
No, because the complexity on Earth has a copy number and an assembly index associated with it, that CA is just a number running.
You don't think it has a copy number? Wait a minute.
Well, it does in the human, where we're looking at humans producing different rules, but then it's nested on selection. So those CAs are produced by selection.
Yeah.
I mean, the CA is such a fascinating pseudo complexity generator. What I would love to do is understand, quantify the degree of surprise in a CA and run it long enough.
Mm-hmm.
But what I guess that means is we have to instantiate, we have to have a number of experiments where we're generating different rules and running them time steps.
Mm-hmm.
But, got it. CAs are mining novelty in the future by iteration, right? And you're like, oh, that's great. You didn't predict it. Some rules you can predict what's going to happen. Other rules you can't. Mm-hmm. So for me, if anything, CAs are evidence that the universe is too big to contain itself. Because otherwise, you'd know what the rules are going to do forever more.
Right. I guess you were saying that the physicist saying that all you need is the initial conditions and the rules of physics is somehow missing the bigger picture. And, and if you look at CAs, all you need is the initial condition and the rules, and then run the thing.
You need 3 things. Mm-hmm. You need the initial conditions, you need the rules, and you need time, iteration to mine it out. Without the coordinate, you can't get it out.
Sure. And that to use fundamental.
And you can't predict it from the initial conditions.
Yeah.
If you could, then it'd be fine.
And that time is
a resource.
Like the foundation of this is the history, the memory of each of the things that created it. It has to have that memory of all the things that led up to it.
I think you have to have the resource.
Yeah.
Because time is a fundamental resource, and I'm becoming. I think I had a major epiphany about randomness, but I keep doing that every 2 days, and then it goes away again. It's random.
You're a time fundamentalist.
You should be as well. If you believe in free will, the only conclusion is there is time is fundamental. Otherwise, you cannot have free will. It logically follows.
Well, the foundation of my belief in free will is just is observation driven.
But I
think if you use logic, it's like logically it seems like the universe is deterministic.
Looking backwards in time, and that's correct. The universe is.